So vast majority of pneumatic systems, right, what we are dealing with is industrial prime movers. We are dealing with something called industrial prime movers. We are dealing with industrial prime movers. So in the industrial prime movers we have, right, electrical systems, hydraulics and pneumatics. So hydraulics is the electrical system is there, hydraulic system is there, and then pneumatic system is there. So here, right, so vast majority of, right, so electrical systems, hydraulic systems they use liquid or either water or something like that. And then pneumatic systems they use pressurized air or compressed air or some nitrogen sort of thing. And then the electrical systems they use the electricity to either, what is the purpose here, either to right, displace an object, or to hold the object with force, right, with force. Then displace an object, hold the object with force. Then what is the other thing? Or compress an object. Compress an object. So either of these things, displace an object, right, compress an object, or to the this one, right, this is, or to compress an object, to displace an object, or to hold an object. So basically we are talking about force. When force is there, this type of, right, scenario comes. So here what we can do is, vast majority of numerical systems use compressed atmospheric air as the operating medium. So when we talk about pneumatic systems in special, when we are talking about pneumatic systems, when we are talking about pneumatic systems, right, so what we can do is, we can talk about air compressors, air treatment, and pressure regulation. Air compressors, air treatment and pressure, air compressors, air treatment and pressure regulation. So this is what is the, right, air compressors, air treatment and pressure regulation. So this is what we are talking about. Maybe if it is upside down also, try to adjust to it today. So air compressors, air treatment and pressure regulation. So what I am trying to do is, I am talking about, when I am talking about pneumatic systems, especially when I am talking about pneumatic systems, right, when I am talking about pneumatic systems, I am talking about air compressors, air treatment and pressure regulation. How to regulate the pressure, how to treat the air, how to compress an air. Okay, so here when I am when I am doing this, so, right, so what we can do is, vast majority of pneumatic systems, when you are talking about pneumatic systems, we use the compressed atmospheric air as the operating medium. So compressed atmospheric air is the operating medium. When we are talking about pneumatic systems, compressed atmospheric air, compressed atmospheric air is the operating medium. A small number of systems use nitrogen obtained commercially from, nitrogen also is there now when petrol pumps are there, when we are talking about filling up air with the vehicles. Nitrogen is also air is there, and then nitrogen is there, air is there. So systems use nitrogen obtained commercially from liquid gas suppliers. So when liquid gas is there, they will take that one and then fill up the nitrogen, and then you pressurize the system, and then so here, so that is what is mentioned, unlike hydraulic system, the fluid is obtained free, and then we can what we can do is we can apply the pneumatic systems and then hydraulic systems. So here, unlike hydraulic systems, what is that one is open. Pneumatic system is open system. What is an open system? Pneumatic system is an open system. Pneumatic system is an open system. So what is an open system? What is a closed system? Hydraulic system is a closed system or open system? Hydraulic system is there. Always there should be some contrast. Hydraulic system. How is the hydraulic system? How is the pneumatic system? So hydraulic system is there. Pneumatic system is there. So when we are talking about hydraulic system when we talk about, that is basically closed system or open system. Hydraulic system is a closed system or open system. Hydraulic system is a closed system or open system. Hydraulic system is a closed system or open system. Hydraulic system is a closed system. Hydraulic system, when we talk about, it is a closed system. When we talk about hydraulic system, it is a closed system. It is water. It is not. We are not getting any. We are not getting any. We are not losing any water. Whatever the water is present before, the same is present everywhere, present all the time. Okay. When we are talking about pneumatic systems, then that is air is flowing continuously. Air is flowing continuously. So that is the air is flowing continuously, coming from outside, and then it is getting replenished. Whatever the air is there, that is going out, and again fresh air is coming. So unlike hydraulic system, a pneumatic system is open. The fluid is obtained free, used, and then vented back to the atmosphere. So unlike hydraulic system, a pneumatic system is open. So unlike hydraulic system, a pneumatic system is open. So open system is there, closed system is there. So pneumatic systems use a compressible gas. Hydraulic systems an incompressible liquid, and this leads to some significant differences. So pneumatic systems use a compressible gas. What is the law? That is when compressible systems are there, compressible gas is there. What is the law you use? Most famous law, PV is equal to, what is the law you use? PV is equal to constant, or pressure into volume is equal to constant. That is Boyle's law we use, right? Air is blowing continuously, and then pressurized air, what we use is Boyle's law. Okay. Hydraulic systems are incompressible liquid, and this leads to some significant differences. The pressure of a liquid may be raised to a high level almost instantaneously, whereas pressure rise in a gas can be distinctly leisurely. Right? So pressure in a liquid may rise to high level almost instantaneously. When we pressurize a liquid, it will like to compress water in some this one. It will compress it. It will get compressed very easily. When you compress it, it will get compressed very easily. High pressure is obtained. But when we compress a gas, it takes long time. So instantaneously that is not there. Instantaneously it will not get compressed. It will take long time, right? So pneumatic systems use a compressible gas, hydraulic systems an incompressible liquid, and this leads to some significant decrease, right? Pressure of a liquid may be raised to a high level almost instantaneously, whereas pressure rise in a gas can be distinctly leisurely. So some time it takes. A reservoir of volume 2 cubic centimeters is connected to a compressor which delivers 3 cubic meters of air measured at atmospheric pressure per minute. Using Boyle's law, the pressure rise is shown in figure 3.1 can be found. So, right, what we take is, right, we are taking a reservoir of volume of 2 cubic meters is connected to a compressor which delivers 3 cubic meters of air. So here the practical consideration is coming. What we are doing is, we are taking a, right, this sort of system we are taking. So here this is the right. So here this is the right. So this is the volume 2 meter cube. 2 meter cube volume is there. This is the delivery. Delivery 3 meter cube per minute, and then this is the inlet. So here this is the system I am considering, right? This is the system I am considering, so that pressure in a hydraulic system can be quickly and easily controlled by devices, right? So okay, now where is the difference coming is, so the pressure of a liquid, whereas pressure rise in a gas may be distinctly leisurely. So as we discussed, if we consider a liquid or water, it can be pressurized very easily it can be pressurized. But if we take a gas, it can be compressed very easily, right? To compress it or to increase the pressure, it takes lot of time. That's why to compress liquid there is no machines, There is no particular machines. If we put some water in the glass and then directly punch it, then it will get compressed. But to compress this, right, gas, we have special systems, air compressors, or we have everywhere. We cannot have, we can have some air pumps which we are used in cycles, specialized systems, because they cannot be compressed very easily, like unlike systems, unlike liquids, which we can increase the pressure. Gas systems like air, they are not like that. The point here is that one. So right, so pressure in a hydraulic system almost, right, whereas pressure in a gas can be distinctly leisurely. So a reservoir of volume 2 cubic meters is connected to a compressor which delivers a reservoir of volume of 2 cubic meters is connected to a compressor. So here reservoir of volume of 2 meter cube, this is the reservoir which will store the air. It is connected to a compressor. This is sort of compressor where we have the inlet of pressure of air, and then this is moving, so just like an IC engine, it is moving from top to bottom, the forward stroke and return stroke, something sort of thing that is moving like that, right? So compressor which delivers 3 cubic meters of air per minute using, right? So what we can do is, this is the piston cylinder arrangement of the compressor. Piston cylinder arrangement of the compressor, and then using which we are storing the air, compressed air in the reservoir. So in this kind of thing, what we can use in this kind of thing is, we can formulate a table using the Boyle's law. What we can do is, what is the pressure range, and then you talk about pressure and volume. So what is the pressure and volume here? Here pressure and volume is, right? So 1 minute volume, right, at NTP, right, P absolute, then P gauge. Always when dealing with pressure systems, we will deal with something like, what is the pressurized system, what is the gauge system, okay, that we will be dealing with. What is the pressurized system, what is the gauge pressure, what is the absolute pressure, right? That we are right, when we are pressurized systems, outside atmospheric pressure is the normal pressure. Then what is the difference? That is called the gauge pressure. So 0, right, 1, 2, 3. So with time, right, so volume is 2, 5, 8, 11, right, 1, 2.5, 4, 5.5. So what is the gauge pressure? 1 means 0, here 1.5, here 3, here 4.5. So this is how you are getting, right, volume 1 at, right, volume with this type of arrangement. When we use, right, with this type of arrangement, we use what I have just shown the piston cylinder arrangement and the right, pressure rise. So here for 1 minute, what is the volume at NTP? P absolute, and then P gauge, 0, 1.5, that is the P gauge. Okay, so that is how the Boyle's law is. What is the use? PV is equal to constant. If you take 1 into 2 is equal to 2, 2.5 into 5, right? Or we can take, right, 2.5 into 5, 4 into 8, 11 into 5.5. So at each time PV is equal to constant. Okay, that is what is the Boyle's law, where we can use it. So meters of air per minute, using Boyle's law, the pressure rise is shown in figure, right, with the volume, right. So with your volume, PV is equal to constant you should apply. PV is equal to constant, right. So that is what is the Boyle's law is used in the case of pressurized systems. So pressure in a hydraulic system can be quickly and easily controlled by devices such as unloading and pressure regulating valves. But here the case is, it is difficult to increase the pressure. It is difficult to increase the pressure, but once you increase the pressure, it is very easy to monitor. It is very easy to monitor the pressure. How? If we keep one regulating valve or pressure valve, right? Like we have here also pressure valve is there, no? Here one pressure valve is there. If you keep one pressure valve here, then that is enough. That is enough to right? That is enough to regulate the valve. That is enough to regulate the pressure. So that is what is the advantage here, right? So, right? So using a regulating valve, fluid is the stored atmospheric pressures and then compressed to the required pressure as needed. The slow response of an air compressor, however, precludes such an approach in a pneumatic system and necessitates storage of compressed air at the required pressure in a reservoir. So the slow response of an air compressor, however, such an approach in a pneumatic system and necessitates storage of compressed air at the required pressure in a receiver vessel. So always we require some pressure at the required quantity. Suppose in your bikes and all is there. So how to storage it? You have to storage at a particular pressure. One part is there, it is at particular pressure. One more part is there, it is at different pressure. That is not the way, right? So volume of this vessel is chosen so there are minimal deviations in pressure arising from flow changes in loads, and the compressor is then employed to replace the air used, averaged over an extended period of time. So the volume of this vessel is chosen so there are minimal deviation in pressure rising from flow changes in loads, and the compressor is then employed to replace the air. So when we are trying to choose the volume, how much volume is required for the compressor, or right, for the vessel, what is the reservoir which I have shown. So it is chosen so that the pressure variations, due to pressure variations, it is right, there is slow variation in the slow deviation in pressure. Okay, so this is right. Deviations in air pressure are smaller and compressor control is easier if a large receiver feeds many loads. So deviations in air pressure are smaller and compressor control is easier if a large receiver feeds. So a large number of loads statistically results in a more even flow of air from the receiver. So deviations in air pressure are smaller and compressor control is easier if a large receiver feeds many loads. So deviations in air pressure are smaller and compressor controller is easier if a large receiver feeds. So if a large receiver is there and feeds many loads, right? So a large number of loads statistically results in a more even flow of air from the receiver, also helping to maintain a steady pressure. On many sites, therefore, compressed air is produced as a central service which is distributed around the site in a similar manner to electricity, gas and water. So what we can have is from the receiver also helping to maintain a steady pressure. On many sites, therefore, compressed air is produced as a central service which is distributed, right? Like we are distributing the fuel from, or whatever the air supply is there, that we are distributing to many cylinders. So compressed air is produced as a central service which is distributed around the site in a similar manner to, right, compressed air whatever is there. So results in a more, how to distribute the pressurized air, like just like you are distributing the air to many cylinders. Okay, so behavior of a gas subjected to changes in pressure, volume and temperature is governed by the general gas equation given earlier as. So what is the equation law is used, that you are using? P1 V1 by T1 is equal to P2 V2 by T2. That is the basic principle you are using. P1 V1 by T1 is equal to P2 V2 by T2. That is the basic principle, or right, ideal gas equation. This equation we use, right? This equation we use ultimately P1 V1 by T1 is equal to P2 V2 by T2. So a compressor increases air pressure by reducing its volume and expression predicts a resultant rise in temperature. A pneumatic system must therefore incorporate some method of removing this excess heat. So what is the right here, like temperature is the main cause. Because of temperature rise, we are increasing the temperature, and then because of that one heat is getting increased, right? So how to remove the heat when temperature is increasing or heat is increasing? How to remove the heat? So a pneumatic system must therefore incorporate some method of removing this excess heat. So whatever the excess heat is there, that we are, right, for small systems, simple fins on compressor will suffice. For larger systems, a separate cooler, usually employing water as the heat removing medium, is needed. So atmospheric air contains water vapor, actual amount varying from day to day according to humidity. The maximum amount of water vapor held in a given volume of air is determined by temperature, and any excess condenses out as liquid droplets, commonly experienced as condensation on cold windows. A similar effect occurs as compressed air is cooled, and if left, the resultant water droplets would cause valves to jam and corrosion to form in pipes. An aftercooler must therefore be followed by a water separator. Often aftercoolers and separators are called collectively primary air treatment units. So here we are talking about right, what is the chapter here in the hydraulics numerators? Just we have seen, right, air compressors, air treatment and air compressors, air treatment and pressure regulations. Air compressors, air treatment and air compressors, air treatment and pressure regulation. Now we are talking about air compressors, air treatment and pressure regulation. So we are talking about air compressors, we are talking about air treatment, we are talking about pressure regulation, how much pressure is needed, right? So here air compressor increases pressure by reducing its creates a resultant rise in temperature. Pneumatic system must therefore incorporate. So we are talking about air treatment, how the air should be treated here. Therefore incorporate some method of removing this excess heat. For small systems, simple fins on the compressor, right? Intermediate in construction air, right? So small systems, simple fins on the compressor. When we are talking about the heat should be regulated. The heat should be regulated. When you are trying to regulate the heat, then the excess heat for small systems, simple fins on the compressor, construction air cooled internal combustion engine will suffice. For a larger system, a separate cooler employing water as the heat removing medium is needed. So atmospheric air contains water vapor, the actual amount varying from day to day according to humidity. The maximum amount of water vapor held in a given volume of air is determined by temperature, and any excess condenses out as liquid droplets, commonly experienced as condensation on cold windows. So resultant water droplets would cause, so what is one example is giving is the maximum amount of water vapor held in a given volume of air is determined by temperature. That is what is the relative humidity. So maximum amount of, he is talking about when I was talking about air treatment. When you are talking about air treatment, air treatment. When we are talking about air treatment, right, what we talk about is water vapor. Water vapor, right? When we are talking about air treatment, we should talk about how much amount of water vapor it can hold. What is the limiting value? So so atmospheric air contains water vapor, the actual amount varying from day to day according to humidity. So right, water vapor, atmospheric air contains water vapor, the actual amount of water vapor day to day according to humidity, that is called the relative humidity, something called relative humidity. Relative humidity, there is something called relative humidity, right? There is something called relative humidity, that is when we are using the relative humidity, concept of relative humidity, it talks about the amount of water vapor held in a given volume and any excess condenses out as liquid droplets. So a similar effect occurs as compressed air is cooled, and if left, the resultant water droplets would cause valves to jam. So what is the thing is air treatment. How to this air treatment comes repeatedly. When we are talking about air treatment, it comes repeatedly in many aspects. When we are talking about air treatment, right, many aspects of engineering it comes. When it comes to refrigeration and air conditioning, or when it comes to right, something like hydraulic machines, in fluid mechanics and hydraulic machines, water vapor treatment, how to treat the vapor, how to treat the surging. So atmospheric air, the actual amount varying from day to day, the maximum amount of water vapor held in a given volume of air is determined by temperature, and any excess condenses out as liquid droplets, commonly experienced as condensation on cold windows. By temperature, and any excess condenses, right, determined by temperature, and any excess condenses out as liquid droplets. Maximum amount of water vapor held in a given volume of air is determined by temperature. So your temperature is increasing when you are compressing something. Your temperature is ultimately increasing. In order to regulate the temperature, you have to use other heat treatment processes. A similar effect occurs as compressed air is, right. So maximum amount of is determined by temperature, and any excess condenses out as liquid droplets. So when more temperature is there, in summer more temperature is there, more humid, more water vapor it can hold. More temperature is there, more water it can hold. And ultimately what happens when a more water it can hold more water, right? It can, when cooled, whatever the water vapor content, mass is conserved, water vapor is same, but when it is cooled, what happens? The water vapor will not escape, but it will start to condense as liquid droplets. Like just on a car we see, right, on the glass of the driving glass of the car, many droplets come, and they will form droplets on the windows, right, glass side of the car. That is nothing but condensation. Because of high droplets are there, then that is forming the condensation. A similar effect occurs as compressed air is cooled, and if left, the resultant water droplets could cause valves to jam. So what happens is, if we are condensing like this in a air compressor unit or in some piston cylinder arrangement where valves are there, if air is coming and then water droplets are coming and then blocking the way, then what happens? The jamming, there was walls are getting jammed. Because of that one, water vapor condensation is happening, and then condensation happens, and walls are getting jammed. Right, walls are getting jammed because of condensation, right? So an after cooler must therefore be followed by a water separator. So after cooler must therefore be followed by a after cooler must therefore be followed by a water separator. Often after coolers and separators are called primary air treatment units. So after coolers and separators are called collectively primary air treatment units. When they are primary air treatment units, when we are talking about primary air treatment units, These are called after coolers and separators. So when we are talking about air treatment, after coolers and separators. Usually this type of thing, right? Chemical engineering also they will try to address these problems, after coolers and separators. Something called unit operations. You can note down unit operations, right? Some sort of unit operations you can use, and then we can see that. Okay, so that is right. Okay, so dry cool air is stored in the receiver with a pressure switch used to start and stop the compressor motor, maintaining the required pressure. So dry cool air is stored in the receiver with a pressure switch used to start and stop the compressor motor, maintaining the right. So dry cool air is stored in the receiver with a pressure switch used to start and maintaining the required pressure. So receiver, right? I have shown what is the right in the previous diagram. You have noted down what is the receiver. So can be directly a reservoir of volume connected with, right? I have told you now per minute using Boyle's law. So response of an air compressor such and so when you are talking about that one are called, right? So receiver, dry cool air is stored in the receiver with the pressure switch used to start and stop the compressor motor, maintaining the required pressure. So ideally air in a system has a light oil mist, right, to reduce chances of corrosion. So when we are talking about the parts of an, right, when we are talking about how the, right, so these are the air treatment system is there, right? After cooler, separator we have discussed, and then we are discussing something like right, some reservoir should be there, some pressure valve should be there. Then the natural question comes, what is the right, how much amount of right, what are the important parts of a compressor, what are the importance of parts of a pneumatic system? So that is the, right, so filter, right, filter is there, then inlet air, right, then so when we talk about okay, so cooler, separator, then receiver, right, then pressure switch, right, motor control, right, motor control center. So motor we are controlling, right, pressure switch, and then receiver, from the receiver we are controlling, and then after the receiver, right, again I am drawing it here. After the receiver we have the secondary air treatment, right, then the load, then the exhaust air. So here how it is transferring an open system compressor, right, cooler and separator, these are called the primary air treatment. right? So this is the motor thing, and then compressor, filter, compressor. So this is the block diagram which will show you what is the right, what are the components where you have the first one, filter, air filter is there, and then through which it is entering inlet air, or from the outside atmosphere inlet air is there. Then after that, cooler, then separator. These are the primary air treatment. Primary air treatment comes. Air treatment, right? We are talking about air pressure, air treatment, and air pressure regulation. Simple. That completes the entire pneumatics part. Then receiver. We are having one receiver. Then secondary, right? Receiver, pressure switch is there. This is the pressure switch. With pressure switch we are having the pressure regulating valve. This is the pressure switch. With pressure switch we are controlling the motor control, and then it is controlling the compressor. It is directly controlling the compressor. How much pressure we want, that much we are regulating with the help of the pressure. I think I did not write here. So pressure switch valve, right? Pressure switch. Pressure switch valve. Okay, so that is the right component parts of a pneumatic system. That are the main parts of a pneumatic system. So here, right, so ideally air in a system has a light oil mist to reduce chances of corrosion and to lubricate moving parts in valves. So right, ideally air in a system has a light oil. So what are the important parts of a pneumatic system or a air compressor system? So basic thing, whether it is a reciprocating air compressor or whether it is a rotary air compressor or blower, something is there. These are the basic parts. It should have a filter, it should have a right primary air treatment purposes like a cooler and then separator, and then it should have something like a one receiver and then pressure switch, motor control valve, then secondary air treatment like after it is increasing the temperature, what we should do, then the load, then the exhaust air, right? So here these are the basic parts when concerned with the pneumatic system, basic pneumatic system, that is dealing with air. So it has light oil mist, like we are having some block diagrams in IC engines also. In a block diagram in an IC engines, some block diagrams are there. Okay, so ideally air in a system has a light oil mist to reduce chances of corrosion and to lubricate moving parts in valves, cylinders, and so on. So this oil mist cannot be added before the receiver, as the mist would from oil droplets in the receiver's relatively still air. So the exit air from the receiver passes through a unit which provides the lubricating mist along with further filtration and water removal. This process is commonly called secondary air treatment. So he is talking about the secondary air treatment. Air in a system has a light oil mist to reduce chances of corrosion and to lubricate moving parts in valves. So how to reduce chances of corrosion? Ideally air in a light oil mist. So oil mist is right, it has some light oil mist. So right, oil mist is oil droplet suspended in air. So what is oil mist system? Oil mist system is a means of governing and generating and transporting a finely dispensed oil from central location to individual bearing housings. Can provide lubrication to 60 pumps and this drives with approximate oil consumption of. So it is a sort of lubrication system. When we are using that one, we are using some sort of lubrication system. Why it is used? From oil droplets in the receiver still air, so the exit air from the receiver passes through unit to the lubricating mist. Further filtration and water removal. This process is commonly called the secondary air treatment. So when oil mist cannot be added before the receiver from oil droplets in the receiver still air, so the exit air from the receiver provides further filtration and water removal. So this cannot be. Oil also you should remove. With oil what we are removing, that is called the secondary air treatment. With humidity, what we are assuming, that is called the primary air treatment. With oil, whatever we are removing, that is called the secondary air treatment. Okay, so like that is the main part. What is the primary treatment part, and then what is the secondary treatment we are using it to function it. Okay, then compressor types, right? Compressor types. So compressor types coming to, as I have told, right, reciprocating compressors are there, and then right, rotary compressors are there. Reciprocating compressor and rotary compressor, both are there. Right, reciprocating compressor is there and rotary compressor is there. Like hydraulic pumps, air compressors can be split into positive displacement, right? Air compressors can be split into positive displacement devices where a fixed volume of air is delivered on each rotation of the compressor, and dynamic devices such as centrifugal or axial blowers. The vast majority of air compressors are of positive displacement type. So positive displacement type is there. Positive displacement type and axial or centrifugal blowers. Positive displacement type. Positive displacement type means displacement type. What is displacement? When we are trying to reach that one, right? Right? When we are trying to reach the the with the help of piston cylinder arrangement, like in IC engines we have discussed. What we have seen, we have some forward stroke and return stroke, that is called the piston cylinder arrangement. So what we have is, you are having something like a positive displacement and dynamic types, reciprocating and rotary types. Okay, there are something like fans, blowers, compressors are there, right? That is the, so rotary compressors are there, fans, something like, right? We can discuss reciprocating compressors and then rotary compressors. So what are the fans, blowers, classification of compressors? What is a fan? What is a blower? What is a compressor? Okay, so that is the thing here. We have to mention what are the stages of air treatment, what are the air dryers. So air treatments, here we will be discussing mostly about the components of air, right? Mostly discussing about the components of an air compressor. How we are discussing an air compressor, and then what is the efficiency, what is a fan, what is a blower, what is a compressor. All these turbo machinery, this is called turbo machinery. All this is called turbo machinery. In modeling and all, what we can use is, right? We can use is the turbo machinery. Okay, there is something called as concept of turbo machinery, right? So that is, So how air treatment we should be, it should be obtained. So what are the compressor types? Like hydraulic pumps can be split into positive displacement devices and dynamic devices such as centrifugal or axial probe. The vast majority of air compressors are of the positive displacement type. A compressor is selected by the pressure it is required to work at and volume of gas it is required to deliver. So compressor is selected by the pressure it is required to work. So pressure it is required to work. Compressor is, so how selected, whether you want a fan, whether you want a, so a compressor, right? Fans are there, fan, compressor, blower. If you see their syllabus also, fan is there, compressor is there, and then fan is there, compressor and blower. Right? Fan is there, compressor and fan, compressor and blower. So what is a fan? So the pumps are there. Pumps are there. Even pumps you have seen in Rankine cycle and all. Pumps also we have seen. Something like pumps we have seen. Pumps also we have seen, right? So here what we can do is, like a compressor is selected, a compressor is selected by the pressure it is required to work at the current volume of the gas it is required to so this is the compressor is selected, what amount of compressor we want, whether we want a right, you want a fan or you want a compressor or a blower, that is selected by the right, that is selected by the type of pressure, what amount of pressure is there, amount of pressure. So vast majority of air compressors are of the positive displacement type. Vast majority of air compressors are of positive displacement type. A compressor is selected by the pressure it is required to work at and volume of the gas it required to deliver. So volume of the gas, compressor is selected by the pressure it is required to work at and volume of the gas it is required to deliver. So as explained in the previous section, pressure in the receiver is generally higher than required at operating position, with local pressure regulation being used. Pressure at the compressor outlet will be the same as that in the receiver is called the working pressure and is used to specify the compressor. So pressure at the operating point is called, not surprising, the operating pressure and is used to specify values and other operating devices. So compressor is selected by pressure in the receiver is generally higher than that required at operating position, with local pressure regulation being used. So pressure at the compressor outlet, which for practical purposes will be same as that on the receiver, is called the working pressure. So what amount of working pressure is required, again how you decide the working pressure, you decide the working pressure by what amount of force we require to, how much displacement should be there, how much amount of force you should hold to require to capture and hold it, and how much amount of force you require to compress it. based on that one, right?